Hello everyone. Let's dive into an important concept in graph theory, the minimum spanning tree, and explore one of the most efficient algorithms to find it, Kruskal's algorithm. Now, why Kruskal's algorithm? Kruskal's is a greedy algorithm, which means it builds the MST by making the locally optimal choice at each step, aiming for the global minimum cost. The key idea here is to sort the edges by weight and progressively add them to the tree, but only if they don't form a cycle. This step-by-step approach ensures efficiency while maintaining the structure of the tree. A spanning tree is a subset of a graph that includes all the graph's vertices and some of its edges without forming any cycle. The properties of the spanning trees are that it is connected, undirected, and it does not contain any cycle. You can create n, c, n minus 1 different possible spanning trees out of a given undirected graph.
Let me discuss some real-life application of minimum spanning tree. The image here shows a layout of houses and a central office. The problem here is the central office needs to connect with multiple houses to establish a telephone network. The left side image shows the direct connection from central office to each houses, which leads to maximum wiring cost. We need to minimize the total wiring cost while ensuring all houses are connected to the central office. This can be done using minimum spanning tree. In the second application, here's a scenario where a city with many houses and unpaved roads. We need to find the best way to pave roads such that all houses are connected while minimizing the number of paved roads or stones required. This can also be done using MST. For a sparse graph, the Kruskal algorithm is considered as an efficient approach to find the MST.
The table. So the first column as the step, the second one as the action that is performed. Next comes the edges connected and then the connected components in the minimum spanning tree. Initially, there is no action and there is no edges connected, and these are the components. That is each of these nodes or the vertex which is present individually initially. So the first step is we have to pick the first edge in the sorted order. That is C and G. We have to check whether the C and G are in different sets. If they are in different sets, then we can connect that edge. So let's check whether C and G are present in different sets. Here, in the initial step, the C and G are present in different sets, and hence we can merge them. And hence the act becomes connect, and the edges connected are C and G, and connected components are A, B, C, G, D, E, F, H. That is, the C and G are connected over here. So next process, the next edge, that is F and G. So here the F is present in different set and G is also present in different set, and hence we can merge these two, and hence we get this. So this particular process proceeds, and in the seventh step, as you can see, that's edge named H and E. This is not connected because in the previous step, H is present in the same set as that of E, as you can see over here. So hence I didn't connect it, and the connected components remains as that of the step 6. And next comes the component of G and D, H called G and D, and hence I'm just connecting it because D is present in the first set and D is present in the second set, and hence we can merge these two sets, and finally all the components in the minimum spanning tree are merged, and hence we can swap the algorithm over here. And also here the total number of edges that is connected are 1, 2, 3, 4, 5, 6, 7.
Hello everyone. Let's see the Kruskal algorithm. First of all, initialize the empty set as A and initialize each vertex as a singleton set using the for loop. Then sort the edges in the graph in increasing or non-decreasing order by their weight. And for each edge in the graph, take each edge in the graph as source and destination vertex, that is denoted as u comma v. Then perform the find set operation of both sets, that find set of u and find set of v. Then check the condition find set of u not equal to find set of v. If it is true, then perform the operations a equal to a union of u comma v and union of u comma v. These operations will perform until all the vertex in the graph are visited. Then return the set A. The set A will contain the
First, sorting the edges takes a log a, where a is the number of edges. Since a is limited by the size of the graph, this simplifies to a log n. Then we initialize n disjoint sets, which takes n. After that, the algorithm performs at most 2a find operations and n minus 1 merge operations, which are efficient and don't add much overhead. Finally, any remaining operations are at most big O of a. When we put everything together, the total runtime is a log n, which is efficient for handling graphs.